Actually,
This sense, right?
no, they're different things.
Okay, so perhaps we should get started then. So it's a pleasure to introduce today's speaker, Janet Anders, who is recently now at Exeter University, and she'll be speaking on thermodynamics of discrete quantum processes. Thank you.
Thank you. Hello, everyone. I'm very, very pleased to be here and be part of this fantastic program. I think it's great that the organizers took the effort to organize the program. So today I will talk about work with Vittorio Giovannetti in Pisa, theoretical work with the title Thermodynamics in discrete quantum processes. I'll also mention some recent experimental work that I've been doing with the group in UCL. By the way, can you guys hear me?
Yes.
Oh, excellent. Right, I also wanted to take the opportunity to advertise a little bit that I'm moving after this meeting to the University of Exeter. So for those of you who have no clue where Exeter is, it's here on the map. So you are here somewhere north of London, right? It's not even on the map, by the way. Exeter's down there. And it's a great place. So it's next to the seaside. It's next to the national parks. It's got the Jurassic Coast, which is just there. So there are a lot of nice places around. So if you want to come and visit and discuss some science, please get in touch. There's funding available. Please just let me know. So here's a picture of the national park to inspire you. And okay, so let me start now with the physics or the maths. I think, in my point of view, thermodynamics in the quantum regime has one big riddle to solve, or at least answer. Possibly not. It might not be possible to actually establish this, but I think the main thing to look at is so thermodynamics is about energy and about separating the energy in two things, heat and work, which we understand intuitively as one thing being useful, the work, and one thing being lost. This is the noise. And so there is a notion of heat and work, obviously, in classical, in very old-fashioned thermodynamics, where we have engines and they work and we calculate efficiencies. And there's also a notion of heat and work in statistical physics. And one of the main challenges, I think, of quantum thermodynamics is actually how do you define heat and work properly. And many people had many ideas about it, and I will by no means give an overview of what other people did and just focus on our approach. But there are many opinions around, and at some point we need to converge on one. So today I will present our approach. And so to motivate our approach, or why do we go the way we do, I'll first give you an overview of what work in statistical physics is. So the idea of a single shot trajectory where you have work defined and then the average of this, and how would you actually measure work in a real system in the experiment. And then the aspiration, I think, that I would like to say that we should try, or which makes sense to try, is to say something about the second law, right? Thermodynamics is about the second law, so can one say something about the second law in quantum thermodynamics, and what can one say? What is irreversibility? What's the notion of it? And then say something about efficiency of engines. So this is the aspiration for me. And the way we go about it is by introducing this discrete quantum trajectory. So there are some subpoints of I will introduce. And with these things, we can actually solve this aspiration. But there's many open questions, and I would be very happy to discuss with you these open questions. Okay, so let me briefly summarize or go through some of the concepts of statistical physics. I hope I don't bore you too much. I mean, this is fairly straightforward things, but not everyone is familiar with this. So the idea in statistical physics is that you have the picture of trajectories in phase space. So here's phase space. There's a position coordinate and a momentum coordinate. You start with some phase space point x0, say, and then you go along a trajectory to some final point x tau in time. And so this can happen with a time-independent Hamiltonian or with a time-dependent Hamiltonian. So for instance, you could think of a harmonic oscillator. I mean, this is just a stupid drawing, but you know, it has some frequency, omega 0, and you could change that frequency experimentally to some other value during which a particle evolves along a trajectory, okay? And then, so this would be then a Hamiltonian, and then the work and the heat are defined for each of these trajectories that the particle takes by the following convention. So you take the Hamiltonian, so for instance, this harmonic oscillator Hamiltonian, and of course, in classical physics, it will depend on the phase space point. So the phase space point appears here in Q and P. And then on top of it, it depends on the frequency that you experimentally modify. So this is called a force parameter in statistical physics. So this is often denoted by lambda. So you take the derivative of the Hamiltonian with respect to this force parameter, and then you take the time derivative, and then you integrate this over the whole trajectory. So this is the statistical physics notion of work. And equally, you can define heat, where here you take the derivative of the Hamiltonian with respect of the phase space variables and then the time derivative. Now, obviously, as you can see, if you take the sum of these two, you just get the full differential of the Hamiltonian. And so, of course, you get the energy at the end of the trajectory minus the beginning. So this is just corresponding to the energy change, right? So this is the first law. And this is the single trajectory picture. Now let me just do a bit of videos because I like visual stuff. So this is a program that came on the BBC last year about Maxwell's demon and the link between information theory and thermodynamics. And really the single trajectory picture is exactly that the Maxwell demon has. Okay, the Maxwell demon sits here and he looks at all the molecules that fly around in the box and sees their motion and can follow their trajectories and can calculate everything basically. So here the video you can see, so the demon just looks and you can see the motion of everything, and then it's also explained how he extracts work from this and so on and so on. So it's very interesting if you want to show this to your students or the general public. This is a great video. Anyway, of course, in the lab we are never actually controlling all degrees of freedom like Maxwell's demon could. We are only interested in averages, and when we speak about work and heat for an engine, for instance, we are, traditionally interested in the average quantities. So instead of doing this picture where you have single trajectories, you average over trajectories. So you might start with a distribution initially, so for instance a thermal distribution, and then you can modify your Hamiltonian along the trajectory, and this kicks the system, of course, out of equilibrium. It evolves according to the new Hamiltonian and ends up somewhere. So the distribution at the beginning goes over into something at the end, and then you can now calculate the average work for this. And one way of doing it is that you actually look at each of the trajectories, you calculate the work for each of the trajectories just as we defined on the last slide, and then you average over all the trajectories that you have gone through, right? So this is then the average work of the whole process. And so a little bit of rearranging, basically just exchanging the integrals, not worrying too much about this, but shows you that you could also, in a way, first take the average of the Hamiltonian with the distribution and then vary this in time. And when you kind of believe this, then you get to this expression that we commonly use in quantum physics, that the work is defined as the trace of the Hamiltonian with the state at each time t, and then you take the time derivative of the Hamiltonian, and you integrate it over time, and that gives you the average work, okay? And so equally you can define the average heat by looking at the time derivative of the state, and when you add them together, you just get again the final internal energy minus the initial internal energy. Okay, so this is the average picture. So that's great. Let me now give two examples. So one of them is a process that is all work. So this is what we call a closed process. It's a deterministic evolution at all times. So each of the trajectories is mapped into exactly another point. And this is a process where the evolution we know in classical physics it's Hamiltonian equations, and in quantum physics we have the Schrödinger equation. So we have this expression for the state evolution, and we can insert it here. And when you do this, you see that the heat, when you insert that there, is obviously exactly zero, because well, the commuter is just so that this becomes 0. And of course, this means that all the work, so the whole process, all the energy that is changed in this process, the closed process, corresponds to work. So it's a trivial example of the split of the two energies. And the other one is obviously an open process. An extremely open process is one where this evolution here is such that the time scale is much shorter than the dissipative time scale, and then you have basically that this Hamiltonian here doesn't really change in time, so this becomes 0. So the work becomes actually 0 in a very strongly open process. So these are the two extreme cases of an all work and all heat process. Okay, let me mention how you actually would measure in an experiment, in a classical experiment, how you would go about in actually determining the work along a trajectory and also the average. Where you do it exactly how the formulas tell you. So this is a real experiment. Let me start with this. So this here is a nanosphere, so it's nanometer sized or micrometer sized in our case, and it's trapped by laser light in a certain way, and it's a harmonic trap. So this particle here sits in a harmonic trap that has such a Hamiltonian, and it's possible to change the trap frequency just the way I explained in the beginning. And when you do this, you can at all times actually observe, classically you can observe the motion of this particle at all times. So you know where it is and what's the speed of it. And you can insert this in your Hamiltonian at all times, so you know the energy at all times. And you can also take the derivatives of the Hamiltonian because you have this external control. You can just calculate all this. And so you can use the trajectory that you measure and the maths together to actually calculate the work in general. And I show you the experiment. So this is not the actual experiment that we use. This is the outreach version of the actual experiment. And so what you're going to see now is, there are two sides here, and the laser comes out there and also on the other side. And in the middle there will be this particle trapped in a second. And it's trapped because, the laser has a gradient, and the particle has a dipole moment, and that interacts in such a way that you get a harmonic trap there. So what you're going to see is now there's some paper, and it burns, and the ash is trapped. I hope you can see it from the back. There's just little particle shining simply through the laser light. So, I mean, this is an experiment that we do. It's classical, totally classical. But it's, there's a laser, right? So it's very classical, and in this case it's obviously in air because someone is actually doing it by hand. In the lab we have this experiment in vacuum, so obviously then the interaction is much weaker with the air and becomes much more isolated. And one day these experiments aim to actually get into the quantum ground state. So it's a harmonic oscillator potential and a motion of this particle here. We can observe this at the moment with a microscope, and one day the hope is that this particle will actually go into the quantum ground state of its own motion. So if it's cooled low enough, the motion will be just in the quantum ground state. This is the big aim of these experiments. Okay, now this was basically the motivation of the work we've been doing. So this was all classical, and so my point of view from where I'm coming is that first of all, there is this idea of trajectories in statistical physics. And so if you wanted to extend this to quantum physics, you already see that it's actually quite difficult if you wanted to do it exactly the same way. That to define work and heat for a general quantum process seems in this approach pretty impossible, given that we don't have trajectories in the same way as we have classically. We do not know where the particle is at all times. We would destroy quantum physics if we observed it at all times. So that's a tricky thing to do. But finding an average work and heat for a general process, quantum process, should be possible. We know generally how to measure things on average. But then we also need to know actually the system at all times. So we need to know what the state is at all times in the Hamiltonian to actually calculate it if we did it the same way as in statistical physics. And then this is a little bit challenging, as in an open system there's actually this question of how would you actually define the system Hamiltonian? Isn't there some ambiguity of defining the Hamiltonian? Okay, so our approach is, okay, we don't want to know things along a whole trajectory at all times, continuously. We will say, okay, we only take discrete steps, because we can also make measurements only in discrete time steps in quantum physics. And so all we want to actually ever speak about is discrete time steps. And see whether we can come up with an average second law for these trajectories made out of discrete steps. Okay, so that brings me to this part now, where we introduce our configuration space. So the first thing that I would like to highlight here is that the whole picture was based on knowing both the particle, so where the state of the particle or the probability distribution of the particle, and also the Hamiltonian. So what is the energetics of the system? So these two things need to come together. And so we start with something that we call the configuration space. So there's one axis that describes the state and another axis that describes the Hamiltonian, and we always need to pair them up to talk about energy. So we have these configurations, there are always these pairs, and we also introduce two special types of configurations, or one actually. So that's the thermal one, obviously. So only configurations are thermal, right? The state is not thermal, because if you don't say what the Hamiltonian is, anything can be thermal, right? So only if you specify what is the state and what is the Hamiltonian can you actually talk about an equilibrium or non-equilibrium state. Okay, and then we want to do trajectories, discrete trajectories between non-equilibrium state and equilibrium state, and then analyze the heat and work for those. Okay, so we will separate two primitives with which we hope then to build trajectories, and these are the obvious ones. So the first one is unitary evolution. So just in the introduction, unitaries will be those that could happen in a closed way, and so the whole energy exchange that happened during such a process will be called work. So we define processes that have an initial state and an initial Hamiltonian, and they go to a final state and a final Hamiltonian, where the constraint is now that the final state is simply unitarily related to the initial state. So that's the only constraint. And we define for these processes that all the energy change that happens during this is work. And then the other process is thermal contact. So you take the state, so you start with an initial state rho and h, and you let the state equilibrate. So what this means is that the final state is required to have this shape for some beta. Okay? So these are the two primitives, and obviously this is going to be a process for which we will assign all the energy change to be heat. So all work and all heat. And so the definition is simply the work, sorry that doesn't read very well, but it's simply the energy change during this process. Okay? So now we want to construct out of these two primitives all sorts of trajectories, discrete trajectories that we can make, and see how the energy balance looks like and whether we can come up with a second law for it. So for instance, you start with a state here that is thermal and another one that is thermal here. How can you get to it? Well, you can construct first a discrete unitary, so that's also called a DUT, and kick the system out of equilibrium. So that blue thing just kicks the system out of equilibrium and then it equilibrates again. And so now you can calculate what's the heat of this whole process. Well, the first step doesn't have any heat. The second step has heat, and we can calculate it. And then the heat obviously depends on the choice of the unitary. So if you kicked it this way, then the heat that you would need to get from there to there will be different than when you hit it a different way. But so there exists also a minimum and a maximum heat. But let's not be concerned about this, because what we also find is that, of course, the entropy change is something that we can calculate. So it's simply the entropy change between the end and the beginning, and you can show that this is simply positive. I mean, this can be lower bounded by this expression, independent of which V you used. So it doesn't matter which unitary you took. This relationship always holds that the heat is smaller than the entropy change.
Okay.
Yeah.
Very stupid question, but can't you use a unitary that just goes from the red dot to the red dot directly?
No, you can't,
So what?
because the state might not have the same entropy, right? So
Oh,
you
I
mean
see.
going from there to there?
Okay, sure.
Yeah,
No,
if the state has not the same entropy, it will not be possible for sure. Yeah, so these can be any pair of states, and we want to connect them. And so this is the simplest way of trying to connect them, by just having these two primitives together. But of course, you can have more steps, right? So now the next thing you think about is, okay, we want to make longer sequences with many steps, and then how does that now change things? If you make more steps, does it change anything? And so actually you find that when you introduce more steps, you can find another sort of Clausius inequality or second law, which is a statement also again about the entropy is always going to be bigger than these components here. So this is a formulation of the second law, and And here, these Q's are always the Q's that appear in each of the red steps, the thermalizing steps, and the betas are the temperatures of each of the thermostates. Okay, so you can make these sequences, and the more steps you make, the more will you actually approach delta S. So you saturate the bound.
Excuse me?
Yeah.
So each step you thermalize with a different heat, with a different temperature.
It can be different, yes. We don't make any assumptions actually on the temperature. They can be all the same, or they can be different, yes. So for each of these, so basically the bottom of this is that when you make any combinations of sequences of these unitary bits and the thermal bits, you'll always have a second law statement of this shape, that the entropy change is bigger than these heat contributions with the temperatures as defined through the trajectory. And you can also show that this bound is saturated. So when you supplement steps in the trajectory, when you go from there to there through just one step, you get some heat contribution, and that is going to be smaller than the entropy. And if you now take an intermediate step here, you go from there to there through this, you have 2 bits where heat comes in, and this is going to be in the middle. So by putting in more steps into the trajectory, you will come closer and closer to delta S. Okay, I mean, that's how it is. And you can then show that, okay, if you take a certain type of thermal steps, you basically then can also show that the entropy change is bounded from below by this, but the entropy change is also bounded from below by something that looks very similar, so this is going to be the same. And there's also a correction, and that correction goes with n, and n is the number of steps. So if you put in many steps, you get this expression as an upper bound, and you see that in the case that when n actually goes to infinity, the lower bound and the upper bound become the same. So in other words, you reach the bound. So you saturate the Clausius inequality, or the second law. And so this is actually a notion of irreversibility. So in the finite case, there's a difference between delta S and this sum. But if you go to n to infinity, they approach each other. But in the finite case, then you can even quantify the amount of work that is being wasted when you don't saturate the bound. So there's an expression that is by David Reed and Michael Wolf that quantifies the waste of work. Okay, so another thing that we looked at is, so originally we started with continuous processes. We wanted to look at continuous processes in phase space, but that's not possible in the quantum regime, so we went to discrete steps. But now we want to see whether there's any way that we can link the two up. And we have so far only proven one direction. So if you have a continuous process that satisfies the Clausius inequality, then you can always find a discrete process that also goes through, that has the same heat and goes through all the steps in the continuous continuous trajectory. But the other way we haven't been able to show yet. So the other way that you can approximate any continuous trajectory with discrete ones is intuitively obvious that you should be able to do it. But we haven't been able to show this yet because it requires a distance measure in this configuration space, and we haven't got this yet. So that's the open thing. Okay, so then. One of the last things is the thermal efficiency. Now, one can look at an engine that is like the Carnot engine and see what is the efficiency if you go through these discrete steps. Let's assume we have a temperature T2, which is higher. So that's this state up here. It's an equilibrium state at this beta 2 higher temperature. And there's another equilibrium state here. And so you go through a machine that goes like this. So you first, it's in equilibrium, then you kick it out of equilibrium, and then you equilibrate it again. And then you kick it out of equilibrium and back. So this is the cycle that we are going to look at. Yes?
I don't see how you change the Hamiltonian, because you apply unitary transformation to a state, but that doesn't change the Hamiltonian. That does a state transformation. Then you equilibrate it again as state transformation.
Well, the Hamiltonian can be time dependent.
So these unitary steps is what? This is some Schrödinger evolution with time dependent Hamiltonian, yes?
Yes, I mean the point is that we don't even want to think about the continuity of the thing, because
how I describe the transition from rho H to rho prime H prime. What's that? I guess rho, you say, in this unitary property, rho is transforms into rho prime by some unitary transformation.
Yes.
How then the Hamiltonian changes? How? It's separate thing? You just separate it?
Oh yes, I understand what you mean. Yes, it's separate. So, I mean, the unitary, for instance, you could think of a closed process in a continuous way. You would think, okay, you start with H0, the system is in equilibrium with H0, but now you're going to change the Hamiltonian in a continuous way from H0 to some HT, and you go and go and go until some H tau, which is the final one.
Mm-hmm.
And then the final Hamiltonian that you would consider the Hamiltonian of your system is H tau. But the evolution is driven by the whole series of H's through the trajectory.
Yeah.
So this is how it could happen.
Yeah. And now abstractly you say I apply any unitary from rho
Exactly.
directly from rho to prime,
Exactly.
and I also change the Hamiltonian the way I want, which is independent actually of this unitary.
Yes, because in fact, I mean, yes, because in fact we can go any way, right? So the initial Hamiltonian and the final Hamiltonian, there are many ways how you can change the initial to the final Hamiltonian, and they will generate all unitaries. Yes.
So how you change it is important, right? Because if it's, for
Yes.
example, changed adiabatically,
Yes.
that will lead to something
Of course.
very different. But now
Of
you
course.
put all those considerations.
Basically, yes, because
Right.
we are not, I mean, if you wanted to do something specific, you have a specific system with a specific protocol, you can calculate some of these things explicitly. But then what we want to do is have a general statement of when the second law holds. And the thing is, we don't need to make any assumptions on what the Hamiltonians are and what the unitaries are. In this setup, for any such trajectory, you get a second law. So it doesn't actually matter.
So when you're talking about the point in this plane,
Yes?
rho 1, H1, that
Yes.
means, what does that really mean? You have a system in a state rho 1 governed by a Hamiltonian H1.
Correct. Well, what does it mean to be governed? I mean, this is partially the problem that I tried to highlight at the beginning. So actually, when you have a system that interacts with the bath, right, you have this, the Hamiltonian consists of the system, the bath, and the interaction Hamiltonian. So how are you going to actually say what is the system Hamiltonian that refers to the system itself? Is it just HS, the bare Hamiltonian, or not? So there's a freedom there that we don't discuss enough. So the Hamiltonian of an open system will be a system, bath, and interaction, right? And so in an experiment, this could be your harmonic oscillator, this could refer to the bath, and there's some interaction. So the experiment that I showed you is of that time. And so what we change is the frequency. So this is something that appears in this Hamiltonian. But if you now only want to look at the system at all times, I mean, we know how you get from a full state to the reduced state, rho s, right? We know that you just take the reduced state and then you have the description of the system. But it's not obvious of how you go from the Hamiltonian that describes both the system and the bath and go to something that is acting on the system. So there's a choice there. And this choice isn't obvious. So in our case, we don't actually make an assumption of how you got to your Hamiltonian. It's what you're going to measure. It's what you're going to measure in the end, so you decide what you think is the Hamiltonian. Okay, so the thermal efficiency again. So this is the low temperature, this is the high temperature, and now you can calculate the entropy change around the circle. Of course, it's going to be 0. And because we know Clausius is correct for all trajectories, and that's a trajectory, we have this relationship. So this 0 is going to be bigger than beta 2 up there, and the heat that is being exchanged when you go from there to there, and beta 1, the temperature there, and the heat that occurs in this step. So this leads to some inequality here. And now, I mean, here you can see that 0 is bigger than this ratio, and this ratio is going to be positive, because for now we just assume temperatures to be positive. So this is a positive thing, so this has to be a negative thing, right? Otherwise this is not true. So this has to be negative, so one of the heats has to be negative and one is positive. And so so one of the heats here, the C3 to C2, will be positive, so this is this one. This is where the system takes in heat, because it equilibrates with the hotter bath. And this one is negative, because here the system cools to a colder equilibrium. And now you can calculate the thermal efficiency. So the efficiency is the work generated throughout this process. So this is the work from going from C1 to C1, actually the negative work, because this is the work done on the system. What you're interested in is the work that's coming out of the system, divided by the heat that's going into the system. So that's the positive one, this one. And so if you work this out, the work is just the change of energy, and there's no change of energy throughout the cycle, plus this heat contribution throughout the cycle, and the heat throughout the cycle is the sum of these two. So you end up with this, and this, gives you just a ratio because we have this equation. So you just end up with this heat efficiency being smaller than 1 over beta 2 over beta 1, which is what you need. And so this gives you the Carnot efficiency already. And so this inequality here is the typical Clausius inequality. And so when you supplement intermediate steps in the trajectory, you will saturate this bound again, so you will get equality there. And so all these inequality signs will become equality signs in this when you saturate. So when you go through the cycle here in a finer way, so you can reach it. You can reach that thermal efficiency. Okay, so actually I'm done now. So the summary of our work is we use two primitives for discrete operations. So one of them is this unitary, and one of them is this thermalizing transformation, and we made discrete trajectories out of them. And we also used the idea of thermal configurations. We simply assume that they exist. And other than that, from the mathematics point of view, we only use that the relative entropy is a positive thing. And with this, we were able to derive a consistent definition of heat and work for all these trajectories, and find a general average second law for discrete quantum trajectories. And we also were able to establish a notion of irreversibility, or reversibility. If you supplement enough points, you reach the bound, and if you don't, you are irreversible. And we also were able to show that the Carnot efficiency can be derived from this alone. So the open question is really to come up with a distance measure in this configuration space that allows you to show that all discrete trajectories, any continuous trajectory can be approximated by a discrete trajectory to show the equivalence. And then also the correspondence to resource theory approach basically we put in the same things. In the resource theory approach, you put in thermal states and unitaries, and so do we, but the approach is still very different, but they come out with similar results. You get the second law, basically. Okay, there are lots of other open questions in my mind. So, for instance, the single shot definition of work and heat in the trajectory picture, I think is very questionable. Exactly how would you define this sensibly? Because, I'm really not an expert, so I would like to discuss this with people. And then also, how would you then extend this to things like Jaginski equation or other fluctuation theorems? And then this best choice of system Hamiltonian. So what do you actually call the Hamiltonian of your system when it's coupled to something? How are you going to measure the energy? This is also something that I think we should discuss. And how do you then experimentally measure the work? So is there some procedure of how are you actually going to measure the work, given that it's a process equality? Okay, so I would like to thank my collaborators on this, so Vittorio and the group in UCL, and I thank you for your attention.
Isn't it that in the Johann Abert paper you have this single shot work, at least in this picture? Where you have I guess. Okay, I don't know really exactly, but I think that's the paper where it should be. I could look there.
What's the name? Johann
Abert. There is this truly work-like extraction. Over.
Okay.
He also has a picture of thermalizations. He uses a model of thermalizations.
And
yes, Hamilton.
Mm-hmm.
Okay.
Oh, sorry.
A general question about this idea of,
Yes.
I mean, these single shot definitions. You're replacing a picture of lots of particles moving around by the average from the trajectory from a single particle.
Yeah.
But then you lose the interactions between the particles.
Mm-hmm. Yes. Yes. Yeah. Yes, it would. Yeah.
Yeah, so can you really recover? I mean, what you...
Well, I mean, basically, I don't know anything truly about the single shot scenario, and that's why I also don't know the reference actually. But basically, from the statistical point of view, I don't understand how you could have a single shot scenario. But I think the single shot scenario that people discuss in quantum physics is a different kind of single shot.
Yeah.
But I think we should discuss this, or Mikhail, it would be nice to discuss
Yeah.
this.
I mean, even the averaging picture can at best produce a statistical physics for non-interactive
Correct.
particles.
Correct. Yes. 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 Yeah. Just a single particle wave function thing. Yes. Mm-hmm.
Yeah, so you said, I mean, the continuous trajectory could be replaced by a discrete one, right?
Mm-hmm.
So how many steps you need?
Well, infinitely many discrete steps. So, yeah.
So that's true for any continuous function, right? Like any continuous process,
Yes.
you can use a
Correct.
discrete process to approximate. But if you take a limit, it's the same. So it's I don't see. So what?
Yes, I mean, in a way, this is what one wants to have. But from the point of view of quantum physics, you cannot. I mean, you don't want to actually look at a continuous picture because it would require you to actually measure at all times. So this discrete the discrete nature we introduced because you only can make discrete measurements, so you can only know the energy at discrete steps.
So if you measure only 5 steps, then it's just an approximation, right? Or you could still
Yes.
have an.
Yes, exactly. Yes. Yeah. Well, I mean, let's say it this way: what is it that we hope to actually get out of thermodynamics? Because I mean, thermodynamics originally says nothing else than okay, there's heat and work, and together they give us the energy. But the main point is that the second law says, well, okay, the heat is upper bounded by the entropy, basically. So this is a statement that we can make as well. So we don't need to actually worry about a lot of the details. If this is all what we want to say in the end, then this is enough. We don't need to say more. So the question is there something more that we want to say, for which we need more detail? Because a lot of the story that is told in standard thermodynamics is not necessary to say the second law is there.
Some people talk about thermodynamics of entanglement.
Mm-hmm.
Do you think these ideas might give a new way of thinking about
Yeah, actually I haven't tried it, but I mean, obviously you could just stick in states that are correlated and then make assumptions about the Hamiltonian and see what this does, but I haven't tried it at all. It would be a good idea to try. Yeah. Mm-hmm.
Okay, so do we have any further questions? Okay, so that's a good thanks, Jen, again.